We have defined the concept of a function f rigorously, as a subset of the Cartesian product of two sets D and R, such that for any x element of the domain D we have a unique element of the range R. In a simplified form, this is expressed by a relation of the form y equals f of x. From this definition of the function, for any value of x we obtain a unique value of y, and we can use the ordered pair, x, y, as coordinates of a point in a Cartesian coordinate system. The set of all these points is the graph of the function. Together with other information, that is points of extreme values of y, sections of straight, curved, increasing or decreasing segments, etc., the graph gives us a picture of how the function goes. Furthermore, a graph may indicate properties of the function which then must be proved or disproved rigorously. A vertical line, that is parallel to the y-axis, cannot contain two or more points of the graph. A horizontal line may contain any number of points of the graph. However, if there is a horizontal line that contains two or more points of the graph, then the function is not invertible. We give a general example of a graph. This example contains almost every possible behavior of the function. It contains straight and curved line segments, points of local minimum and maximum, isolated points, a point of inflection and a vertical asymptote. This graph must be studied carefully, since parts of it may appear in many graphs representing specific functions. Let us see now some specific examples of graphs. The first example is for the graph of an even function. Such a graph is symmetric with respect to the y-axis, that is, the y-axis acts as a mirror for the graph. For every point of the graph, its symmetric image with respect to the y-axis belongs also to the graph. The graph of an odd function follows in the second example. Such a graph is symmetric with respect to the origin O of the coordinate system. For every point of the graph, its symmetric point with respect to the origin O belongs also to the graph. In the third example we have the graph of a function f of x in red. If we add a constant c to the value of the function, we obtain the same curve translated upwards by c, as it is given in blue in the figure. If we decrease the independent variable by c, we obtain the same curve translated to the right by c, as it is given in green in the figure. In the fourth example we have again the graph of a function f of x in red. If we replace the independent variable x by c times x, then we shrink the graph horizontally by a factor 1 over c. Thus we can have the behavior of the function in a larger interval of x. For c equals 3 we obtain the blue curve of the figure. In the fifth example we start with a function whose graph is given by the red curve. Every horizontal straight line cuts this curve only at one point. Therefore, this function has an inverse, represented by the graph of the blue curve. The red and blue curves are symmetric to each other with respect to the green line, that bisects the 90-degree angle of the x and y axes. Finally, in the sixth example we have the graph of a periodic function. As we see, the graph consists of a part that is repeated many times as x varies. The period is the smallest positive number t that satisfies the relation f of x plus t equals f of x. In our case the period is about 3.14.